everyone, and welcome to another episode of Interstigation. In today's episode of Interstigation, I will go over a to the x derivative, and that is on top of e to the x derivative that we talked about 2 episodes ago. So over here I have a daily problem, and this problem will certainly not appear on any of the tests because this is very easy problem, and it can be solved instantly with logarithm identity. But this is to kind of verify that our identities that we derived from 2 episodes ago is correct. So what we have over here is to find the derivative of this thing using both logarithm identity and the chain rule. So obviously it is very easy to do with logarithm identity, and so we can manipulate this as x times the ln of e. Well, this is just equal to ln of e, which is just equal to 1, so that's just equal to x. And if we want to take the derivative of that, then we can simply get 1. And the other side, it kind of is more complicated and overdoing things that we don't need to, but that is just a verification that our derivative derived for e to the x and ln of x is correct. So the other side, we can just take the derivative and kind of bash it out. Obviously, this is not a recommended way of doing this on the test, but as I said, this is just a verification. And using the chain rule, we can have that is the derivative of this thing with respect of the inside function. So that will be 1 over e to the x, because the derivative with respect of ln to the x is equal to 1 over x, and the derivative with respect of e to the x is equal to e to the x, and times the derivative of e to the x, so that is just e to the x, and we get 1. And we got the same answer for both sides. So that made sure that this problem we got it correctly, and the previous rules that we got is also correct. And let's proceed with today's rule. Today's rule, we want to differentiate this as a to the x, where a might not be just e, it can be any basis. So the a can be, we can differentiate 2 to the x after this lesson. How do we do that? Obviously, we are going to base it on top of e to the x that we did 2 episodes ago. So if we want to write a as some sort of e, so that would be equal to, so if we want to make it some base of e, and that would be e to the ln of a, because ln of a would just be log with base of e of a, and this result to the as base of e would just turn it into a. Therefore, we will have a is equal to e to the ln of a. We can use that later. If we want to differentiate this thing, then we can simply rewrite this. Well, this may look very complicated, like we are overcomplicating things, but no, because we only know the derivative of e to the x, and that's actually pretty clean. So we just have this. And if we want to switch the places, well, this is possible because you can just unpack this as e to the ln of a times x and move this in front and add a parentheses. So then you would simply get this. So that would be the derivative with respect of x of this e to the x with a power of ln of a. And how do we do that? We can use the chain rule. So we can use the chain rule on this thing so that we get stuff that we want. So over here, we actually want to see this as a function. So we might not necessarily need this, so we can make this function. So e to the x times ln of a, and let's see this as x. So let's take this f of x, which is equal to this. The f of x is equal to x times ln of a, and g of x is equal to e to the x, and we can use the chain rule on top of that. So that will be equal to the derivative with respect of that, so that's just e to the x times ln of a times this derivative. This derivative, obviously, we can use the constant multiple rule, that is. So that is just equal to ln of a. And if we unpack this as e to the ln of a to the x, then we figure out that the thing inside the parentheses is just equal to a. So that will be a to the x. So that will be that. That will be a to the x times ln a. And we are done. Thank you for watching this episode of Investigation, and I will catch you in the next one where we go over log a of x with random basis. Goodbye.